Hi there. This video is on section 11.10. It is where we learn about Taylor series and how to apply algebra and calculus on those Taylor series. I'll talk a little bit more about Taylor series and what they are, but I'll just kind of make a note that perhaps Taylor series is the most important topic that one learns in a Calculus 2 class. It is generally how we take any kind of function, as long as we can find a derivative. So any kind of differentiable function, as complicated as it may be, and we can write it as a simple polynomial. It is a quite marvelous kind of idea because it can be very difficult to anti-differentiate complicated functions, find limits or derivatives of complicated functions. But for a polynomial, that's just like x to the n. That we have a power rule. The antiderivative of x to the n is x to the n plus 1 over n plus 1, as we've done many, many times. So very, very simple to anti-differentiate, differentiate, etc. polynomial functions. So this process we're going to be talking about today really is the crux of that big idea. Okay, so let's just kind of look at some basic ideas of what a Taylor series is. And that's right down here. So we're going to learn how to write a function as a power series. That's called a Taylor series. A power series, we studied that in the previous section, looks like a constant plus a constant times x plus a constant times x squared. That's a power series, also known as a polynomial. It's kind of infinitely long polynomial, so I guess technically when people hear polynomial, they think it stops at like x to the fifth or x squared or something. These power series, they go on for as long as necessary, off to infinity. Um, there are a lot of letters here. And so let me just clarify that there's an input variable called x, an output variable called f of x, or sometimes written as y, and all the other stuff in there are just constants. The c's are constants, the n's are constants. The n's help us determine the value of c, but really this is just a equation that looks rather more complicated than it really is. It's x is the input, y is the output. Okay, although we are going to practice computing some Taylor series by hand, all the elementary functions that you've learned in pre-calculus and beyond have known Taylor series. So once we get an idea, once we get our feet wet a little bit with how Taylor series are created, we probably won't do them ever again because we'll use the known Taylor series of all the elementary functions to create new Taylor series of functions we don't already know the power series for. Okay, so what does a Taylor series look like? Well, it is a power series, right? So just remember, power series has a constant plus a constant times x plus a constant x squared, et cetera, right? It's just the power series thing. The Taylor series just tells us how to find the constants. So the constants for a Taylor series, if we have a starting value as 0, which is very, very common, then the function has the first constant f of 0. It has a second constant, the derivative evaluated at 0 divided by 1. The second constant, that's C2 there, I guess is the third constant, 0, 1. Third constant here is the second derivative evaluated at 0 over 2 times 1. And you might be able to see the pattern. The next one is the third derivative evaluated at 0 times 3, 2, 1. Then it'll be the fourth derivative evaluated at 0 times 4 times 3 times 2 times 1. And generally, it's written in closed form like this: the nth derivative evaluated at 0 over n factorial. And of course, it's times x to the n because that's the x part for our polynomial. Now, sometimes we don't have 0 as our center point for where our polynomial is. And so we would shift it to the right or the left by a units. If we shift it to the right or left, we get a very, very similar looking Taylor series, which is this bottom box here. But instead of just x to the n, it'll be x minus a to the n. So x minus a squared instead of just x squared, x minus a cubed instead of just x cubed. And we evaluate all the derivatives at a instead of evaluating at 0 because we're not at 0 anymore. We're at that magical location a. So I'll show you an example of each of these where we center at 0 and where we center in a non-zero number and how to create those. And then afterwards, I'll show you how to use our known Taylor series to create new ones. And I'll show you a couple things in between as well. All right, so let's get going with the lecture. All right, so my first example is compute the Taylor series for this function cosine x at a center point of 0. Okay, so for this problem right here, we're going to use our formula from the previous page, but you're just learning this, so you may not remember all the things. Essentially, the way I'm going to have you kind of think about it in terms of trying to help you remember is we did in a previous section a local linearization. We used a line to approximate a function, y equals mx plus b, or b plus mx, I think, or b plus ax is the way the book wrote it, something like that. We used a line equation to approximate a function. And the line was determined, or at least it was partially determined by the derivative. So we used the derivative to help find the line, the tangent line, and we used the tangent line to approximate the function. Well, why just use a line to approximate a function? Can't we use something a little more curvy to approximate a function? For example, can you use a parabola to approximate a function? And the answer is yes, you can. But a parabola, which is an x squared equation, requires knowledge about the second derivative as well as the first derivative. And we don't have to stop there. We can do a cubic equation, which we have to know about the third derivative and the second derivative and the first derivative, or you could do a fourth degree quartic equation, and you'd have to know about the fourth derivative, third derivative, etc. So that's the idea in this this formula down here. If you look at the formula, right? So this is the formula I'm talking about. Whoops. So we have the first derivative that helps us determine the number in front of x. That's our linear component. We have the second derivative that helps us determine the x squared part. That's the parabola component. Then we have a third derivative that does the x cubed or cubic component, etc. So you need the nth derivative to help you determine the coefficient on the nth exponent on x. And the bottom is just, the factorial. So either 1 factorial, 2 factorial, 3 factorial, which is just like 3, 2, 1, or 3 times 2 times 1, or 4 factorial would be 4 times 3 times 2 times 1. I'm not saying you need to memorize this, but sometimes it helps that it's not just a jumble of random numbers and letters. That you have an idea of what's going on. Oh, I'm doing the third derivative. This is going to give me the x to the third constant. Okay. So I'm going to recreate this a little bit over here. We have a function. It's written in terms of some constant. Let me put me over here. It's written in terms of constant, and that's just the linear term, or the constant term. And then the linear term, I have a c1 times x, and then I have a c2 times x squared. But these constants aren't just random. We know exactly how to find these constants. This would be the c0 would be the function evaluated at 0. And then c1 is going to be the derivative evaluated at 0. And then you have to divide by 1 factorial, which in this case is 1, so it doesn't really do anything. But we'll just do it so we can see the pattern. The next one is the second derivative evaluated at 0 divided by 2 factorial, which is 2 times 1. And then we're going to keep going on and on and on. All right, so to write our Taylor series for cosine, we need to find the value of the function at 0. So our function is simply cosine x. And I'm going to be finding the value of the function at 0. Let me put it off to the side over here, actually. I'm going to find the value of the function at 0. And then to find the next term, we have to find the derivative. So we have to find the derivative of the function. And likewise, we'd have to find the derivative at 0. And we'd keep doing this. I'll do it just for a few times so that we can kind of get the idea of how it works. For the homework or for a test or something, they'll tell you to keep going until you get to the power 5, the 5th degree polynomial. Or they'll say, go until you get like 3 non-zero terms, or they'll be specific about how far to go. I'm just going to not specify that. I'm just going to try to help you understand what's going on for this one. And for each of these, of course, we're going to try to find out the corresponding derivative at our center point, which in this particular example, and most examples, is going to be 0. So this is supposed to be like the derivative, the 4th derivative. This is like the 5th derivative at 0. Okay, so I have set up what I need to find. So I'm going to go ahead and find it. All right, so they usually put like parentheses around some of them. I don't know. So what is the derivative of cosine? Well, we remember those from our elementary derivative formulas. That's the negative sine x. And what's the derivative of negative sine x? Well, the derivative of sine is cosine, so this would be negative cosine x. And what's the derivative of negative cosine x? Well, we know the derivative of cosine is negative sine, so it's negative negative sine or sine x. Or sine x is cosine x. And it kind of repeats itself a bit. Derivative of cosine x is negative sine x. If I do the next one, which would be the sixth derivative, that would be negative cosine x. So you can kind of maybe see that it keeps repeating itself because, the derivatives are kind of going back and forth between sine and cosine. All right, so if you have a chart, if you have a calculator, or if you just remember some of the basic calculations, we need to find the value of the function at 0. So cosine is the x value at 0 radians. The x value is over there at 1. So f of 0 is 1. The derivative equation is negative sine x. Sine is the y value. So the y value at 0 radians, the y value is 0. So this is negative 0 or just 0. Then we have negative cosine of 0 for our second derivative, which is negative 1. Sine again is 0. This is where it starts repeating. The fourth derivative is the same as the original function. So I can just repeat the 1 there. And then it's going to be 0. And if I want one more step to the sixth derivative, I would get negative 1 again. So it kind of repeats like that. All right, so let's write our Taylor series. We have all the numbers. These numbers are the C values, the constants, or they help determine the C values, the constants in front of all the X values. So our function, which is, I'll write f of x here, is cosine x, our function, is equal to the value of the function at 0, which is just 1, plus the derivative at 0, which is 0 over 1 factorial times x, but that's all going to be 0, so I don't have to worry about that. Plus, and I'm going to have to get a little bit more space to the right, so my screen over a little bit like that, and maybe shrink down a little bit. Okay, so that's the linear term. That's the f prime. F prime of 0 was 0, so we get 0 over 1 times x. F double prime is the x squared term. Oops, I forgot my x squared up here. Maybe someone realized that and said, where's your x squared term? There it is, right there. F double prime of 0, well, that is a negative 1, right? That's f double prime of 0. So this is going to be negative 1 over 2 times 1. That's 2 factorial, x squared. Then we have the x cubed term. What's the third derivative? It's 0. So this is going to be 0 over 3 times 2 times 1, which is going to be 0, of course. Then we get the x to the fourth term. So x to the fourth term, we have to use the fourth derivative to find the constant for that. The fourth derivative is 1. So that's going to be 1 over, well, it's going to be the fourth factorial because it's the fourth exponent. So 4 times 3 times 2 times 1, and etc. So we keep going. I'll go to the next two because I have them written out here. The next one's going to be a 0, x to the fifth, and this is over 5 factorial. And then the last one's going to be negative 1. So the sixth derivative is negative 1. So to find the coefficient on x to the sixth, I have to use the sixth derivative, which is going to be negative 1. And it's over 6 factorial, which is 6 times 5 times 4 times 3 times 2 times 1. Big number. Okay. So let's straight mark. So this is the unsimplified version of my cosine Taylor series. If I just kind of clean it up a little bit, I have a 1 here. 0 over 1 times x is 0, so I don't have to include that because it's just 0. So it has no linear component. The x squared term would be negative 2 over 2 times 1, which is negative 1/2. Instead of writing a plus negative, I'm just going to write minus 1/2. X squared, that's my x squared term. For my x cubed term, the coefficient is 0, so I don't have to include that. For the x to the fourth term, I have x to the fourth, and what's my number? Well, the number on top is 1, and the number on the bottom is 4 times 3 times 2 times 1, which is 24. Then I have another 0 term, and then I have x to the sixth, which is a minus 1 on the top and a very large number on the bottom. So 4 times 3 times 2 times 1 was 24. So I have 30 times 24. So 3 24s is 72. And then another 0 on there. So it's 720 is the answer here. You could check my work with your own device if you like. But and then of course it keeps going, goes on and on and on and on forever. So that is the Taylor series for cosine x when we have the center of 0, right? When all the values we plug in are 0. I'll talk about in a moment what that center of 0 really means, like why does it matter? But I want to show you the technique for computing a Taylor series of a function at a particular point. We've also talked about how to find the interval of convergence in a previous section. The interval of convergence is found just by doing the ratio test. To use the ratio test, we have to have like a formula that we can plug in. So we need a formula for this cosine x thing. And if you haven't done that before, it can be a little bit difficult to try to like back solve to like figure out what do I do here. You might notice that the exponents are only even numbers. So when I do an x, I can't just do x to the n because that will include all of the numbers. What we do to have only the even numbers is we have x to the 2n. All right, this is a capital N, 2n. So that way, when n is 0, you get x to the 0. When n is 1, you get x squared. When n is 2, you get x to the 4. So it just makes it always even. 2n is always even. The series does go from positive to negative to positive to negative. The most common way of making things go from positive to negative is just by putting a -1 to the n in there. That makes it go positive to negative. We have to make sure it lines up. So this is the n equals 0 term. When I stick an n equals 0, -1 to the 0 is positive, so that's nice. This would be like the n equals 1 term. So if I stick n equals 1, I get x squared, and then -1 to the 1 is odd, so it checks out. If it didn't check out, you just have to throw another -1 in there, like -1 in front, or mostly mathematicians put like a -1 plus 1 in the exponent, saying there's another -1. So you just have to double check that it starts with the right positive negative version. And the bottom, we had the 0, 2, 24, 7, 20. If you remember, those came from 2 factorial, 4 factorial, 6 factorial, right? So this here, 2 was 2 factorial, this was 4 factorial, this was 6 factorial. Those were those numbers came from. And so we can now think about the fact that the formula is going to have a factorial in it. And in fact, it's always going to have even numbered factorials. 2 factorial, 4 factorial, 6 factorial. So we end up having a 2n factorial here. And once again, you can double check. When n is 1, we get 2 factorial. When n is 2, we get 4 factorial. When n is 3, we get 6 factorial. And so our series is the summation of all of these things right here. So this is the closed form of the cosine function. And we need a closed form in order to find the interval of convergence, because we're going to be using the ratio test to find the interval of convergence. And the ratio test, if you want a recall here, you look at the limit as n goes to infinity, and you take the n plus 1th divided by the nth ratio, x plus 1 over nth ratio, and you try to find out when that is less than 1. When it's less than 1, we get a converging series. When it's greater than 1, we get a diverging series. If it's equal to 1, we don't know either way. Okay, so at this point, I'm going to show you that one of the documents I have for you on Canvas that you can download if you wish is a chart for the common polynomial series, the polynomial approximations for functions. So I'll zoom in maybe a little bit here. E to the x, this is the polynomial, and this is what the closed form of it looks like. And for sine x, it's this thing. Cosine x is the one we just did. So this is the known Taylor series for cosine x. 1 minus x squared over 2 plus x to the fourth over 24, et cetera, et cetera, et cetera. Here's the closed form for it, which actually is the one that I just showed you on the lecture notes page. And it does give you the interval convergence as well, but we'll do that ourselves to verify that in a moment. So all the different series, all the different elementary functions are all listed here. Some of them we don't have enough math to get the closed form of, so they're not going to ask you to find the interval convergence or inverse sine, because we don't, at this point in our math studies, don't know how to write the closed form of the series. So don't worry about that until you get to a future class. But for a large part of things, we're just going to be referring to something like this, a list of known Taylor series. And the cosine one we just did is listed there as well. And we kind of know the answer is going to be negative infinity to infinity. I'll show you what that is in a moment. So before I show you that, let me show you one more nifty little thing here about cosine. Remember, cosine is 1 minus x squared over 2 plus x to the fourth over 24 minus x, right? It keeps going on and on forever. And this is centered at 0. So I'm going to talk about what centered at 0 means at this point. So here I have on Desmos, move me back over here. On Desmos, I have a little app here that shows you the cosine wave. This is cosine. And it's going to show you different Taylor polynomial approximations for this. For example, if I just go out to the x squared term, so I'm not going to go out like all the way to x to the sixth or x to the 10th or anything like that. I'm just going to start at n equals 2. So I'm only going to the constant term and the x squared term, which is going to be 1, and then minus 1 over 2 times x squared. And I'll show you what that looks like right there. So this blue thing right here is just the x squared, the constant plus the linear plus the x squared. It's that second degree approximation to cosine. And you can notice at 0 or even near 0, they're basically identical, right? So all these values near 0, the parabola, which if you're color sighted is in kind of a bluish purplish color, and the original function, which is above it in red, or if from a distance, the red is the curvy one and the parabola is the one that's going down, right? So the parabola, the x squared, is a very good approximation as long as you're pretty close to x equals 0. At x equals 0, the y value is 1, and they look pretty similar until you get maybe over here at like negative 3/4 or positive 3/4. It looks like it starts diverging a little bit. We can notice that it is getting a separate. And now we can always approximate errors and things like that, but we're not going to do that for this particular section, this particular class. So let me bring the number of degree up to 4. End of the third is 0, so I don't need to have end of the third. I'm going to go up end of the fourth. So end of the fourth means we're going to have an x to the fourth term. And if you remember the x to the fourth term, well, that's just x to the fourth over 24. So I'm doing 1 minus x squared plus x to the fourth over 24. So I'm doing all the way up to x to the fourth in this visualization. And now you can see that the curve here, which is like an x to the fourth curve, is also very, very close. In fact, it's close to the function for a much further distance. So of course it's close as before, but now it's close all the way to maybe like negative 1.25 or something, all the way to positive 1.2 or something like that, right? So now it is going to match up for a lot more values that are close to our center point of 0. So our center point is where we're going to be expanding out from, and we need more and more terms to get a better and better approximation, especially if we're moving away from the center point. So I will include, back up a little bit here. Whoops, back up a little bit here. So that's the cosine wave is this guy right here. And the fourth degree polynomial certainly doesn't match up over here, but close to 0, like all this section right here, looks really, really close. So let me do a 6th degree polynomial. And now you can see it matches up for a lot further. It matches up all the way to like 2.5. Here's an 8th degree polynomial where it matches up a lot more, even maybe to negative 3 to 3. 10th degree polynomial. So the idea here is the more, the higher the power or the more terms that you include in the power series, the polynomial approximation, the more that the graph will match up exactly for a wider interval of numbers. And of course, if we go off to infinity, we will get exactly matching for as long as the interval of convergence of the series is. Now, the interval of convergence of cosine, I mentioned before, was negative infinity to infinity. So it turns out that you can always use this Taylor series polynomial to approximate any cosine value to any degree of accuracy. You want 100 decimal places of accuracy, no problem. We just need to include some more Taylor series polynomials to get that degree of accuracy. But we can get any degree of accuracy for any value as long as we include a long enough Taylor series polynomial. And of course, all those calculations can be done quite easily using a computer. So we can, therefore, with technology, get any degree of accuracy using our polynomial instead of our cosine function. All right, so that's a lot of asides there with the idea, but I want to give you a kind of visual about what it kind of means to be a polynomial approximation, a Taylor series, and what the centered thing means, and also to refer to this reference page that I think you will find very handy, or if you have another one, it'll have some similar types of elementary functions as well for you to use. All right, back to the lecture notes. All right, so we do have this closed form that I found over here that matches up with what the reference sheet says. So let's do the ratio test. The ratio test says I have to do the limit as n goes to infinity of an plus 1 over an, and I have to see when that's less than 1. Okay, so I need a little space. So I'm going to do it over here. I'll just rewrite the limit as n goes to infinity. I'm going to put me back over here, I guess, of an plus 1 over an, and I want to find out when that's less than 1. So an plus 1 and an I get from my formula. That's why I need a closed formula. An is exactly the formula, and a plus 1 is the same formula with n plus 1 plugged in there instead of just n plugged in there. So we get the limit, and we get some big fraction. On the bottom is just the regular series. And on the top is the series with n plus 1s plugged in instead of n. So I literally just plugged in n plus 1 when in place of n every single time. So now we're going to simplify this limit so we can actually find that result. So let me point out, first of all, that these big bars here are absolute value bars, which means that we can get rid of anything that's negative. Absolute value bars means we're going to make the distance to 0, which is always positive, or just get rid of all the negatives. So -1 to the n plus 1, it's either -1 or +1. If it's -1, we make it a +1, which means it just multiplies and doesn't affect, just like a +1 would not affect anything. So we can get rid of these negative things. The other ways, I'm going to write out a little bit. So on top, I'm going to flip and multiply too. So on the top is x to the 2n plus 2 over, this is 2n plus 2 factorial. And the bottom, I'm going to do instead of dividing by that fraction, I'm going to multiply by the reciprocal. So the 2n factorial will now be on top, and the x to the 2n will be on the bottom. And in fact, I don't even need the absolute value bars anymore because everything's positive. Okie dokie. So believe it or not, these things simplify quite nicely. You may remember that from previous homework assignments you did. So x to the 2n plus 2 and x to the 2n. There's a whole bunch of x's on the top, a whole bunch of x's on the bottom. There's more x's on top. There's 2 more x's on top than there are on the bottom. So if I'm going to divide out, I divide out all the x's, and I'm left with 2 of them. Or if you want it to be more like algorithmically or formula based, you just subtract the exponents. You have two powers, they have the same base. You're dividing those powers, you subtract the exponents. So I'll write the limit. I guess I do need the absolute value bars because it has to be absolute value less than one. I'll put them back there so I don't forget at the end when I'm trying to figure out the actual interval convergence. Um, okay, anyway, I'll leave them there for now so I don't get confused. So I have this limit. I have x squared is the number of x's left over. Then I have a bunch of factorials. I have 2n plus 2 factorial on the bottom, and I have 2n factorial on the top. And let me just remind you, 2n factorial means you start with 2n, and then you multiply by one smaller than that. So 2n, one smaller would be 2n minus 1, and then one smaller would be 2n minus 2, and you go all the way down to 1. 2n plus 2 factorial would be 2n plus 2, and then you multiply by one smaller than that. What's one smaller than 2n plus 2? That's 2n plus 1. And then one smaller than that would be 2n, and then 2n minus 1, et cetera. Da, 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 da. So if you kind of look at the stuff here, the factorial stuff, a lot of stuff matches up. Like you have a 2n and a 2n that matches up, a 2n minus 1, a 2n minus 1. There's a 2n minus 2, and there'll be a 2n minus 2. Like all the stuff is going to divide out except for this 2n plus 2 and 2n plus 1 on the bottom. So over here, I have a 2n plus 2 and a 2n plus 1. So that is how my complicated ratio test limit simplifies. Now, x is just a variable. It doesn't have anything to do with n. N is the thing that's going to infinity. So we have, in some sense, the x squared we don't really care about. We have 2 times infinity plus 2, and we have 2 times infinity plus 1. So this is tending to x squared. I'll leave over there, and I get infinity times infinity on the bottom. Right? So if you have anything divided by infinity, that's going to be 0. So this is going to equal 0. So when is this less than 1? So for which values of x is this less than 1? It doesn't matter what value of x we use. If x is, like, say, 3, then you get 3 squared, but 3 squared over infinity is still 0. If x is 10, you get 10 squared over infinity is still 0. So I don't care what value of x you have, this will always equal 0, and 0 is always less than 1. So it converges for all values of x. And the way we write that mathematically, I guess I have to make that disappear for now. It converges for all values of x. So we write the interval of convergence, interval of convergence would be negative infinity to infinity, all values of x. And the radius of the convergence would be infinity. Half the distance is the radius. So the interval of convergence negative infinity to infinity. So the radius is also infinity. So there's the confirmation that the interval the interval of convergence for the cosine Taylor series is all values of x, negative infinity to infinity. And just to remind you, I was just kind of verifying this idea of the cosine having this Taylor polynomial series. This is the closed form, and this is the interval of convergence. So all these different kind of functions are on here for your reference. Okay, so hopefully you got the idea of that. We're going to do one more example of computing a Taylor series. We're going to do it where the a value isn't 0, so you can see one of those. So my next example is to compute the Taylor series for the natural log function ln x at a center point of 1. So we're going to use a equals 1 as our center point. Okay, so there's kind of a routine where you have to write out each of the derivatives. So the original function, whoops, not at 0, original function evaluated at 1, the derivative evaluated at 1, the second derivative evaluated at 1, right? We're going to be using each of the consecutive derivatives to find each of the consecutive constants in front of that degree of the polynomial. I guess I'll stop at 4 because that's how much space I have here. And now for each of those, we have to find the value of the function. Oh, these are supposed to be x's. I got to first find the derivative, Jim, before you plug in the 1. So first of all, I got to find all the derivatives. These are all x's in here. And then I got to plug in the 1. So I can find f of 1. I forgot my whole process here. You got to find the derivative, then plug in 1. Or the original function, plug in 1. Find the derivative, plug in 1. Find the second derivative, plug in 1, etc. All right. That's the same as what we did before, but we found the derivative and then plugged in 0 instead of plugging in 1. So up here, we found each of the derivatives, which was, of course, an equation. And then we plugged in the value we're centered at, which was 0 in our first case, right? And in this case, we're not centering at 0, we're centering at 1. So like above, like the one in example A, we find all the derivatives, and then we plug in the center point, which is going to be 1. So here's all the derivatives, and we're plugging in the center point of 1. So the original function is just ln x. The derivative ln x is 1 over x like this, or we can write it as x to the negative 1. I'm gonna do it like that because it's just a little easier to see the derivative. The derivative of the second derivative, which is the derivative of the first derivative, is the derivative of x to negative 1, which is negative x to the negative 2. The third derivative, I'd have to differentiate this thing. I bring down the negative 2, so it becomes positive 2x to the 1 smaller exponent, so negative 3. Then I bring down the negative 3, so I get negative 6. X to the negative 4th power, etc. So I can keep finding derivatives, and then I got to plug in the value at 1. So f of 1 is the natural log of 1. The natural log of 1, if you remember your log values or what a natural log function is, it's going to be 0. You can check that on a calculator if you like. The first derivative value at 1, that's just going to be 1 to the negative 1 power. Well, 1 to any power is just 1. So we'll write that as 1. And then we have the second derivative evaluate 1, which is a negative 1 to the negative 2. So 1 is being raised to the negative 2. And then, of course, there's a times negative 1 in front of it. So 1 to any power is 1 times negative 1 is negative 1. Do a couple more here. This is going to be 2 times negative 1 cubed, or to the negative 3rd power, which is going to be 2. And then we're going to get negative 6 times negative 1. Why am I saying negative 1? I don't know why I'm saying negative 1. You're asking me, where did the negative 1 come from? And that's, my imagination is where it came from. We're plugging in 1. We got to plug in the value of A. We got to plug in the center value. So we're going to plug in 1. I think I got confused with the exponent and the value we're plugging in. So sorry about that. All right, hopefully you can see my error and fix it on your notes if you're taking notes along this. We're plugging in 1 each time. So I didn't make any mistakes. 1 to the negative 3rd power is 1 times 2 is 2. 1 to the negative 4th power is 1 times negative 6 is negative 6, etc. Okay, so let's write our Taylor series. So you could refer back to the previous Taylor series or the first page where I've written out the Taylor series. Moving back over here. I wrote out the Taylor series when it's centered at like a non-zero number, like at 1. So the only thing that changes is that you're not going to have x to a power. You're going to have x minus a, or in this case, x minus 1 to a power. So x minus 1, x minus 1 squared, x minus 1 cubed, x minus 1 to whatever power. And then the way we find the constants is we don't plug in 0, we plug in the value a, which was 1. So finding the constants, you plug in the a value of 1 in this situation, and then it's going to be times x minus a instead of just x. So a very similar formula, but you do got change what you plug in, and you don't just write x to the end, you write x minus 1 to the end. Okay, so I go over here. All right, so my function, which is the natural log function, is equal to the constant term. The constant term is 0, right? That's the function evaluated at 1. And then I plug in the x to the first power thing. So the constant for x to the first power is 1. And remember, it's always over that like n factorial thing. So 1 over 1 factorial. If you look before, I just wrote over 1, but it was the constant 0 over 1, the constant over 2 factorial, the constant over 3 factorial. So maybe I'll just be consistent and write this over 1 because that's what 1 factorial is. Then we get the next and then we have to have x, but remember, it's not just x, it's x minus 1. Okay, then we have the next constant, which is negative 1, and that's a 2 times 1, and this is the second power on x. Wait, I'm not keeping track of my numbers very well. Hopefully, I find all my mistakes. X minus 1 squared. Next is the third. We're doing the x to the 3 term, so we need the third derivative, which is a positive 2. And then that's over 3 times 2 times 1. And that would be x minus 1 cubited. And we'll do one more. The fourth one is negative 6. So the next term here would be a negative 6 over 4 times 3 times 2 times 1. And then we get the fourth degree, which is x minus 1 to the fourth. And we can keep doing this forever and ever. So that's what the Taylor polynomial, the Taylor series looks like for our natural log x function centered at 1. Let's clean this up a little bit. So 1 over 1 is just 1, and then we get x minus 1. Negative 1 over 2 times 1 is just negative 1 over 2. This is the next term is 2 over 3 times 2 times 1. The 2's divide out, so we're left with positive 1 over 3. So that's a 2, by the way, over here. Okay, now it looks even less like a 2. 2. This is 1 over 3. Then we have our third degree here, x minus 1 cubed. This is negative 6 over 4 times 3 times 2 times 1. It turns out that if you do this all out, this is like the 3 times 2 is 6, which divides out with 6. You get negative 1/4. Let me get rid of the positive and write that as a minus because it's going to be a negative term. Minus 1 over 4, x minus 1 to the fourth. And you might start to see the pattern. It is going from positive to negative, positive. So it's another alternating series. You have all these x minus 1s to a power. And then the number is just, well, it's 1 over here, I guess. And then it's 1/2, 1/3, 1/4, 1/5. So again, not so easy to figure out what these series, to back develop these series. But we do have an alternating thing. So we're going to do negative 1 to the n. And we'll change it to n plus 1 if we need to, just to make sure it starts at the right place. We have x, we'll change it to n plus 1 if we need to. Then we have x minus 1 to the power of n. But that's assuming we start with n equals 1, right? We don't have an n equals 0 term, so let's start with n equals 1. So for n equals 1, we have x minus 1 to the 1. Let's check our sign here. Negative 1 to the 1 is negative, but our first term is positive. So we are going to have to add this plus 1 in there. And what does that do for us? Well, when you plug in n equals 1, when you plug in n equals 1 into this formula, you get negative 1 to the 2 power, which is positive, which matches up with this first term, which is a positive. If you stick in n equals 2, you get 2 plus 1, which is third. Negative 1 to the third exponent is a negative, which matches up with our second term right here. So each time you put the n in, you get the right sign, positive or negative. So if you're trying to develop these formulas yourself, you're going to have to double check that the negative part starts in the right place. And if not, you just put a plus 1 up there to shift it over a little bit. All right, so our x minus 1 to the n, that's x minus 1 to the first, x minus 1 to the second. And what about our number on the bottom? Our number on the bottom, I guess I do want to do this here. The number on the bottom is what? Well, in the first case, there was nothing on the bottom, which is, by the way, like a 1, all right? And the second case, a 2 is on the bottom. then we have a 3, then we have 4. In fact, if you kind of notice, the exponent number matches the number on the bottom. The denominator matches the exponent each time. So our exponent was n, so what goes down here is n as well. And that's the closed form, that's the series form for natural log when we're centered at 1. Okay, and then we can find the interval of convergence just by doing the ratio test on this little series right here. So by the way, this is the answer to the Taylor series. This is the Taylor series right here, written out to the 4th power. So this is a 4th degree polynomial approximation for ln x. And then the closed form is like this, which you can use to write out as many terms as you want, or you can also use it to find the interval of convergence using the ratio test. So let me do that computation real quick. I'm going to get rid of the negative signs because they are going to be insignificant. When we talk about absolute value bars, they all become positive. So I get x minus 1. I need some more space here, I think. I get x minus 1 to, I'll put the bottom one first. The bottom one is x minus 1 to the n over n. So the top one is the same thing with n plus 1. So instead of x minus 1 to the n, it's x minus 1 to the n plus 1. And instead of n on the bottom, it's n plus 1 on the bottom. So the an is just the exact same series as we have here. I threw away the negative part. And the an plus 1 is exactly the same as the an thing, except that I'm going to put an n plus 1 everywhere I see an n. So now I'm going to simplify this by converting division into multiplication by using the reciprocal. So I get x minus 1 to the n plus 1 over n plus 1. And this thing gets flipped to n over x minus 1 to the n, like that. I have a bunch of x's on the top, or a bunch of x minus 1s on the top, a bunch of x minus 1s on the bottom. So I can simplify these exponents by subtracting or just recognizing that I have one more on the top than I do on the bottom. So this is going to be our limit. All that's left on the top is n and x minus 1 to the 1. And on the bottom, I have n plus 1. All right, and we want this to be less than 1. Less than 1 is where it converges. Okay, so what is this limit going to be? Well, remember, the x's don't have anything to do with n, right? So the x's don't care. They're going to be there no matter what. But the n over n plus 1, those are the things that we need to see what happens when n goes to infinity. So as n goes to infinity, what happens to n over n plus 1? Well, you may sort of note on the side if you want. I mean, a lot of people could see this already, but if you can't see it, you could just write it out. N over n plus 1 is that limit right there. And you can like see that it goes to infinity over infinity. And you can reason out that the highest powers of n are the same. So it'll be the coefficients, or you can use L'Hopital's rule because it's an indeterminate form. And L'Hopital's rule will give you, well, the derivative of n is 1, derivative of 1 n is 1, and derivative of 1 is 0. So you get 1. So this n part thing right here, let me do it in green, I guess. This n part here will go to 1. The x minus 1 doesn't care because there's no n's in it. So what you get here is you get, I'm doing the limit, so you get 1 times just x minus 1 to the first power. It has to be less than 1. So that's where this thing converges. It converges when the ratio test is less than 1. And it converges for this result of the limit, right? So, well, the one we don't care about, so we need to find out when the absolute value of x minus 1 is less than 1. And if you remember how I recommended you do this, some people know this immediately. They know the interval is from 0 to 2, but if you're not that sort of expert with absolute values and inequalities, remember you can just put this center thing between the plus and minus of this thing. So this is 1, so you put negative 1 and 1, and you put less than signs, and you put x minus 1. So the simple, TLDR to solve this is just put the thing between the positive and negative of the number on the right-hand side. And then we use algebra. So to get x by itself, I'd have to add 1. But if I add 1 to this side, I have to add 1 to this side. And I would also add 1 to this side, because there's kind of like two different equations there. So add 1 to both sides twice, or all three sides once. And that gives me, well, negative 1 plus 1 is 0. X minus 1 plus 1 is just x. And then 1 plus 1 is 2. So that's my interval of convergence. I do have to test the endpoints, because the endpoints we don't know about. So the endpoints are x equals 0 and x equals 2. So we might, like, if like 2 worked, we would put like a equal to here, like it works for 2. If it doesn't work for 2, we would just leave it as a less than, right? So that's the testing the endpoints, which you also did in a previous section. So how do we test the endpoints for a Taylor series? It's basically the same way we did before. We take the original series, which is, where's the original series? Here it is. Take the original series, and we plug in those values of x to see if it converges or not. So for x equals 0, I'm going to plug that in. So I get the series from n equals 1 to infinity. This is still negative 1 to the n plus 1. There's no x's to plug in. I plug in x there, so I get 0 minus 1 to the n. And the bottom I have n. So that's the x equals 0 version. When I stick in x equals 2, I have this series. Let me put it in a different color, maybe. I have this series, n equals 1 to infinity, negative 1 to the n plus 1. When I stick in x equals 2, I have 2 minus 1 to the n. So that's going to be 2 minus 1 to the n, which is just going to be like 1 over n. All right, so let me test each of these real quickly. For this one, I have negative 1 to the n plus 1 and negative 1 to the n. So negative 1, so I'll do an aside over here. Note. Negative 1 to the n plus 1 times negative 1 to the n. Well, this will always equal to negative 1. Why? Because one of these is always positive and one is always negative. Right? So because one of them is like to an even power, one's to an odd power, they're going to switch back and forth. And when I multiply a positive 1 times a negative 1, I get a negative 1. So this thing right here, on the one on the left-hand side, it will be just negative 1 over n. And I'll leave this to you to do the steps, but this converges by the alternating series test. The three things you would need to verify, this is like a test. Does it, oh no, it doesn't alternate. This is not an alternating series test, this is always negative 1. So ignore what I said because it was wrong. This does not alternating series test. It has to alternate from positive, negative, positive, negative. This is just always negative. This is just always negative, right? So this does not alternate. This is just negative 1 over n. So negative 1 over n diverges. And diverges for several reasons. You could do the p-series test, or you can do like harmonic series. You could even do an integral test. Right, all those tell me that that thing diverges. And over here on the x equals 2 side, we have negative 1 to the n plus 1, negative 1 to the n plus 1, and then we have 2 minus 1 is 1, 1 to the n. Well, 1 to the n is always n. 1 to the n is always 1. It never, never, never changes. So this negative 1 to the n plus 1 goes back and forth. 1 to the n is always 1. So multiplying by 1 doesn't do anything. So this is the one that goes negative 1 plus 1. I remember one of these alternates, and it's the x equals 2 one that alternates. So simplifying this series, the top part, negative 1 to the n plus 1 times 1 to the n, ends up being negative 1 to the n plus 1. And the bottom is n, and this converges by the alternating series test, which is what I was trying to throw at the first one, which was wrong because it doesn't alternate. This one does alternate. To do the 3 steps alternating series test, You have to check that it alternates, which is what the -1 to n plus 1 does. You have to check that the terms get smaller. So the denominator goes from 2 to 3 to 4. So when the denominator gets bigger, you know the terms get smaller. And lastly, you'd have to check that the limit goes to 0. Take the limit of this thing, it ends up being like 1 over infinity, which goes to 0. So it does check all 3 boxes for the alternating series test. I'll let you verify those for yourself. If it was on a test, you'd have to like tell me, show why, give some justification or show the steps of why it converges by the alternating series test. And of course, we also showed why this diverges because of any number of tests. This thing diverges. So according to our interval of convergence, the x equals 2 converges and the x equals 0 does not converge. So over here on my answer for the interval of convergence, 0 to x to 2, I would include 2. So I put an equal sign there. So that's my interval of convergence from 0 to 2, and half that distance is the radius, which is 1. So the interval of convergence is from 0 to 2 for the Taylor series for the natural log function centered at 1. So this doesn't have a ton of values that it converges for. You'd only really want to use this Taylor polynomial for the natural log function if your values for x are somewhere between 0 and 2. It definitely converges between 0 and 2, but it's not going to give you an answer that's a good estimate if you're outside this range. Okay, so let me zoom out a little bit so you can kind of see all the writings I did for this page here. I'm not sure if you can see that, but maybe you could take a screenshot and zoom in a little bit. Zoom and enhance, I guess, is the terminology. So this is the idea of computing a Taylor series by hand, and then also seeing if you can find the interval of convergence. And again, all these are kind of written out here. You can see the ln x centered at 1 is already written out here. It's a pretty common one that you'll see. That's the closed form. And there's the interval of convergence, which we actually did confirm was 0 to 2, not including 0, but does include 2. All right, so you'll do a few of those in the homework just to show that you kind of understand the idea of computing a Taylor series. But generally, we don't do a lot of these by hand. It's just a lot of tedious work that doesn't really do much because we already know the Taylor series for them. So on my last page of the lecture notes, I'm going to show you sort of some of the ways we write Taylor series out without doing them all by hand and what we can do with these Taylor series. So that, in fact, is what I'm calling applying algebra and calculus on Taylor series. So we're going to do a few examples of this. So the first example is use known Taylor series to write the Taylor series for this function here, h of x, centered at 0. So remember, the idea is to write a polynomial. We want to write a polynomial that is the same as this cosine x cubed function. Now, cosine x cubed is a combination of two functions. It's a combination of the cosine function and an x cubed function. Mathematically, we call this the composition of functions, right? The composition of those two. Now, x cubed is already a polynomial. It is x to the third. So the thing we have to worry about is the cosine. How do we write the cosine in terms of this? Well, we did that already, actually, right? We already wrote cosine. That was our example A, I think, in terms of a Taylor series polynomial. And it came out to be 1 minus x squared over 2. I'm going to write the factorial in there, even though 2 factorial is the same as 2, just so you guys can see the pattern. X to the 4th over 4 factorial, x to the 6th over 6 factorial, etc. Yeah, I have a lot of these memorized because they come up a lot. So yeah. All right. So let me write the closed form as well. We came up with a closed form for this thing, which was the sum from n equals 0 to infinity of -1 to the 2n, because we had to only do even powers, and then we had x to the 2n, and then over here we had oh no, not -1 to the 2n, -1 to the n, because we do need it to alternate. And -1 to the 2n would always be even, so it would always be like a positive number. We don't want to always be a positive number. we want it to alternate. So it's -1 to the n. That alternates between positive and negative. The exponent has to be 2n because we need it to be even number. And the factorial on the bottom is always an even number as well. So it's 2n factorial. And once again, this is on our reference page, so you don't have to memorize this. You can just go to the reference page and write it down from there. So you don't need to have done this by hand. You don't need to redo it by hand. You can just look it up and say, okay, this is the known Taylor series polynomial for cosine, and this is the known closed form for cosine. All right, so we got it. So this is cosine. Now we're looking for cosine x cubed. So we want to find cosine x cubed. How do we find the Taylor series polynomial for that? Okay, so I'll put the question mark over here. Well, believe it or not, this is an equation. Cosine x equals 1 minus x squared over 2 factorial, etc. That's an equal sign, right? So whatever we do to one side, we can do the other side. Like if I can add 7 to one side, I add 7 to the other side, it's still an equation, it still equals. If I substitute x equals 4 on one side, I can substitute x equals 4 on the other side, it's still equal because it's an equation. Well, I don't want to substitute x equals 4. I want x to be x cubed, right? I literally want to change x to x cubed. This is the algebra thing called substitution. You've done this in many, many situations before where, instead of finding f of x, you found like f of x cubed, right? You just plug in x cubed in place of x, and you get your new function for f of x cubed. That's all we're doing here. Instead of just having x as our input, we want x cubed. So we just put x cubed in there. So this is going to be 1 minus x cubed squared over 2 factorial plus x cubed to the 4th over 4 factorial minus x cubed to the 6th over 6 factorial. And I'm not going to do the 8th. I'm going to write out I'll write dot, 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 so you guys know it's dot, dot, dot. And I'm going to write out the series for this. Now, it ends up being just as easy to write this out because once again, we're just plugging in x to the 3rd. So you don't have to worry about all the different parts because there's only one place to plug in x. It's where the x is, right? So instead of x to the 2n, you have x to the 3rd to the 2n. And all the other stuff stays the same because there's not x's there. They're just n's, right? And n is not what we're doing. We're changing x to x cubed. So that's the Taylor series for cosine x cubed. You just plug in x cubed. And if we had combinations of things, we would just do combinations of things. We can add functions together. We can compose functions together. We can multiply functions together. So whatever you need to do, you just do them with a known Taylor series. Any kind of funky Taylor series you're asked to find, you take the elementary known ones and just manipulate them algebraically until you get what you want. In this case, I just substituted x cubed in for x, and I got the Taylor series for cosine x cubed. Let me clean this up a little bit so it looks a little nicer. Cosine x cubed. This is going to be 1 minus x cubed squared. Got to multiply those exponents out, so I get x to the 6th over 2 factorial. Then I have x cubed to the 4th, so x to the 12th over 4 factorial, etc. And the closed form is equally easy to get because we already just substituted x cubed in there. So you have a -1 to the n, that didn't change. You have x cubed to the 2n. X cubed to the 2n, you multiply those exponents together, and you get x to the 6n. And this is over 2n factorial. And that's the closed form for cosine x cubed. You're just literally just doing algebra on these Taylor polynomial equations. Okay, so question part E said, use known Taylor series to write the Taylor series for this function hx equals cosine x cubed, centered at x equals 0. This is what it looks like written out in terms of a few polynomial terms all the way up to x to the 18th. And this is what it looks like a closed form, just like that. All right, so we can write other kinds of functions as a Taylor polynomial, right? We can write these even more complicated things than just cosine, like cosine x cubed, or anything else we dream of. We can just use algebra to combine them together to be able to write out the Taylor series. What else can we do? Well, we go to example F. Example F says, find the integral from 0 to 1 of cosine x cubed dx. So I would like you to maybe try for a little while to see if you can do cosine x cubed using integration by parts, or partial fractions, or whatever substitution, whatever technique you want to use. You won't be able to do it. You can't integrate cosine x cubed using the elementary sort of techniques that we learn in calculus 2. It's very, very difficult using any type of calculus, as a matter of fact. However, using Taylor series, it's really easy. So how do I say that? Why do I say this? Because we don't have to actually integrate cosine x cubed. We can integrate the Taylor polynomial that's equal to cosine x cubed. So the integral of this thing from x equals 0 to x equals 1 of cosine x cubed is the integral of 1 minus x to the 6th over 2 plus, that should be I think that's a 12 down, a 2 there. The 1 disappeared. So x to the 12th over 4 factorial. 4 factorial is 4 times 3 times 2 times 1, which is 24. And then you get minus x to the 18th over 6 factorial, which I believe is 720, etc. By the way, in closed form, it's equally easy to do in closed form as well. We're going to have the integral from n equals 0 to infinity of the integral of negative 1 to the n x to the 6n over 2n factorial. 2n factorial. Now we do need a dx over here, and we do need a dx over here, so I'll put this all in parentheses so it's all looking mathematically correct. So we're integrating this thing, cosine x cubed times dx. So this is the cosine x cubed part times dx. This is the cosine x cubed part times dx. And now we can just integrate. So I do know what the integral of 1 is. That's just x. I know what the integral of x to the 6th is. That's x to the 7 over 7. And I still have that 2 down there. And then the next term will be x to the 13 over 13 times 24, etc. Right? So I can integrate this, and I can do this as long as I want. And the more terms I use, I'm up to x to the 19th already, but I can keep writing out more and more terms. And the more terms I write out, the closer the approximation will be for a wider interval of numbers. Okay, I'm having a hard time making this look nice. Or my version of nice, since nothing I write is really all that nice. There we go. 19 times 720. Plus, 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 plus. We do need to have a plus c at the end, but we are evaluating this from 0 to 1. So as you might know, you don't have to write the plus c because it'll add to 0 if you're going from x equals 0 to x equals 1. In closed form, well, what does that look like? Well, we're still doing all the different things. So we still have this summation thing. And then we're integrating with respect to x. Again, there's a lot of letters that are kind of confusing. So just kind of remember x is the variable, right? F of x is the output, x is the input, right? So when I'm integrating with respect to dx, the only thing that is x to the 6n, right? So that's the thing I'm anti-differentiating. So the antiderivative of x to the 6n is going to be x to the 6n plus 1 divided by the 6n plus 1. The other stuff is constants. Constants are not affected by antiderivatives or derivatives. So the negative 1 to the n will still be there. The 2n factorial will still be there because they're just constants. But the x thing, I'll have to make one bigger exponent. And I'll have to make a 6n plus 1 on the bottom. So that's the closed form version of the integral of cosine x cubed. We do have to plug in the values x equals 0 and x equals 1. And so now let's go ahead and plug in the values. If I plug in 1, so if I plug in 1, what do I get? I get 1 minus 1 to the 7th is 1. So 1 over, I'm still going to write this as 7 times 2. I know it's 14, but I don't want to do all the other numbers, so I'm just leave them unmultiplied. This is 1 to the 13th, which is 1 over 13 times 24. This is 1 over 19 times 720, etc. So that's when I plug in 1, and then I subtract when I plug in 0. But you notice when I plug in 0, all these things are 0. 0 minus 0 plus 0, blah, 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 blah. Right? So I just get this thing right here of, I'm running out of room, so I'll just box it here. This is the answer right here as the answer plus dot, dot, dot for the area under the cosine x cubed between x equals 0 and x equals 1. In other words, the integral of the cosine x cubed graph between 0 and 1 is this polynomial, or I mean this series of a bunch of fractions, 1 minus 1 over 7 times 2 plus 1 over 13 times 24, etc. If I add all those numbers up, I get the exact area under the curve, or between the cosine x cubed graph and the x-axis. And in closed form, I get a closed series. Again, when I plug in 0, I'm not going to get anything because all the things are 0. 0 to any exponent is 0. So I just have to plug in 1. And that's going to be n equals 0 to infinity, negative 1 to the n, 1 to the 6n plus 1, but 1 to any power is just 1. So I'll just leave this remnant as a 1 so you guys can remember that I actually did it. It's not just like it vanished. It's 1 to a power, so it's just 1. And on the bottom, I get 2n factorial and 6n plus 1. And so if you can find the sum of that series, that would be the exact value of the integral. But typically, we're not going to find the exact value. We're going to find an approximation by using a whole bunch of terms. And the more terms you use, the better the approximation. Already with 4 terms, we're getting x to the 19th. We're getting a 19th power approximation just by using 4 terms, which is usually pretty darn good. But we can get any number of degrees of approximation. We can get any number of decimal places of approximation just by adding more terms. And once again, technology is very good at doing all these number crunching fractions for us. So you just tell technology to add it up to, the 10th term or the 20th term or the 100th decimal place or whatever you need to do. And it'll do so, and you'll have your answer to this integral problem to whatever degree of accuracy you like. So there's a simple example of how we can do something which would be generally very, very difficult. Finding the area of this function or the antiderivative of this function evaluated between 0 and 1 by hand, or even using technology to help you, is very, very difficult. But by using a Taylor series, it's very, very simple. And of course, we can even use Taylor series. We can even use technology to help us do the Taylor series. So it's not like you have to do the Taylor series by hand either. All right, I have one last example for you just to kind of show you it's not just integration that we do. So I have this limit problem. Limit as x approaches 0 of cosine x cubed minus 1 over x to the 6th. So we're going to do a limit problem using a Taylor series polynomial approximation. We should check to see what happens when we do direct substitution. So let me do a direct substitution. So I get x equals 0. So if I stick in x equals 0 just to see what happens when I directly substitute the value of x into the equation, I get cosine of 0 minus 1 over 0 to the 6th, which becomes 1 minus 1 over 0, which is 0 over 0. So 0 over 0 is L'Hopital's rule, or at least is something that we know we now can use L'Hopital's rule on. So we could use L'Hopital's rule and differentiate this. And it ends up, when you use L'Hopital's rule, you take the derivative of the top, the derivative of the bottom, it ends up still being 0 over 0. So you have to do L'Hopital's rule again. And you may have to do it several times. And each time the derivatives become much, much more complex because you start having lots of like chain rule type things and product rule type things. So you get chains and products of chains. And you can do it, but it's way easier if you use a Taylor series polynomial to do it instead. All right, so we know what cosine x cubed is. Cosine x cubed, it's up here somewhere. Cosine x cubed is this guy right here, 1 minus x to the 6th over 2 factorial plus x to the 12th over 4 factorial, etc. So I'm just going to use the Taylor series in place of x cubed. So we'll get, let's try in blue, I guess, limit x approaches 0. Cosine x cubed is 1 minus x to the 6th over 2 plus x to the 12th over 24 plus, oh, yeah, minus, I guess, minus x to the 18th over 720, etc. And then on the bottom, you have this x to the 6th thing. Oh, sorry, you get this thing minus 1 on the top. On the bottom, you have x to the 6th. All right, so let me just double check I did this right. I have the limit as x approaches 0 of cosine x cubed, which is this giant thing in parentheses, minus 1 over x to the 6th. I took this guy and I wrote it using the Taylor series polynomial in place of cosine x cubed, because they're equal to, right? This polynomial thing is equal to x cubed, so I know the limits are equal. All right, so how is this any easier? Well, it simplifies quite nicely. So let's see, there's a 1 here and a minus 1. Those go away. And then I have an x to 6 that I'll write it out a couple steps, although maybe some of you can see what's going to simplify very quickly. I get x to the 6th over 2 divided by x to the 6th. So the x to the 6s are going to divide out. I get plus x to the 12th over 24 divided by x to the 6th minus x to the 18th over 720 divided by x to the 6th, etc. Some of you may have simplified this by factoring. It comes out the same way, whichever way you want to do it. All right, so here, x to the 6th divided by x to the 6th is just 1. So this becomes the limit as x approaches 0 of just 1 over 2. Here we have x to the 12th and x to the 6th. We have two powers that have the same base, so we subtract the exponents. So here we get x to the 6th. There's more x's on top than on the bottom. So x to the 6th over 24. Yeah, that's right. That's right. And then the next one's minus. There we go. Minus. And this is x to the 18th over x to the 6th. Once again, you have two powers, have the same base. You subtract the exponents. You get x to the 12th over 720, etc. So I just plugged in my Taylor series in place of cosine x cubed, and I simplified just by like combining like things. Combine the 1 and minus 1, combine the different x things together, and I'm left with this equivalent limit. Well, let's find out now what happens when you do direct substitution. Turns out we don't have to do anything like L'Hopital's rule for this problem. If we use direct substitution, that means we're plugging in x equals 0, right? Because that's what the limit's going to x equals 0. So the first thing has no x in it, so it's 1/2. The next thing is going to be 0 over 24. 0 to the 6th is 0. The next one is going to be 0 over 720, because 0 to the 12th is 0. I don't care how many other terms you're going to have 0 over something. Or they're all going to be 0 forever on. So what does that limit equal to? 1/2 plus 0 plus 0, I guess minus 0. Anyway, it's a half, right? You're adding zeros. So the limit is equal to 1/2. And we didn't have to use any kind of derivatives, product rule, quotient rule, chain rule, whatever. We just plugged it in and simplified and got our answer of 1/2. So that's an example of how you can use a Taylor series polynomial in place of a function to just do algebra calculus, right? So we did the integral problem, which is a calculus problem using Taylor series polynomial approximation, and we did a limit, which is a calculus problem using a Taylor series approximation for cosine x cubed. Okay, so there's a couple of examples of using or how Taylor series is used. It has lots and lots of other kinds of applications. Taylor series is the first of 3 types of approximations to functions. I say approximation, I mean, it's an equivalency, it's equal to, but you usually stop at some point. So if you stop at some point, you only get like, 8 decimal places of accuracy or whatever, 25 does. You're going to stop somewhere to get some degrees of accuracy, whatever you like. That's why they technically call it an approximation, because we typically stop at some point when we're satisfied with the accuracy. So the 3 basic types of function decomposition. Taylor series is the one that you come across, and it's used very widely. And you're writing a function in terms of a polynomial, in terms of x's. The second type of one that you'll see if you do extra credit or if you do next semester calculus is called a Fourier decomposition. So Taylor series decomposition we study a lot in this class. Fourier series decomposition, we just kind of touch on if you want to, but that's decomposing a function into a series of sines and cosines, which sounds a little weird and burdensome since sine and cosine aren't the easiest function to understand. But anytime you have a signal, if you have any understanding of physics or engineering, signals are waves, right? And so anytime you have a signal, cell phone signal, television signal, whatever you have, or even literally ocean waves, decomposing those into sines and cosines is very easy and very, very accurate. And it's actually typically better than converting them into polynomials. So if you have wavy type things, you do a Fourier decomposition. And if the third type of thing, which is more recent, is called a wavelet decomposition. And that's a little more advanced. And that's things that are kind of wavy, but they stop. Like signals, they wave forever. So imagine your wave and then it kind of dies off, right? So if you have a wave that dies off, you could use a Taylor series approximation, Taylor series polynomial. It's good. It's not the best. You could use a Fourier series approximation, a Fourier series decomposition, and that works, but it's not the best. You could also do a wavelet series decomposition or a wavelet polynomial or wavelet function decomposition, which turns out to be the best for those types of things. And the wavelets use like baby bell curves. If you know statistics, like a normal curve, a bell curve, kind of looks like this. It has the equation e to the negative x squared. Those types of things, I know it looks confusing. Like, why would you ever want to convert things into those? Well, if you do a little bit more math, which I hope you do, then you'll learn that converting these sort of more complicated wavy things that die down into these baby bell curves ends up being super efficient and much more accurate and easy to do. Um, we're just doing Taylor series, but I thought I'd use this as an opportunity just to kind of give you a little hook for the future if you do want to do more math or physics or engineering or one of those sciences that does a lot of function decomposition. That's what you're looking forward to. So anyway, hopefully this video was interesting, helpful, useful. And if you do have any questions, please do seek me out so I can help you out if you want to do more example problems together, etc. And I hope you have an enjoyable day.